Welcome to this lecture series in linear algebra. In this lecture, we'll be proving a cornerstone theorem, which is the cyclic decomposition theorem. And a lot of material that we have been building was towards this theorem. It is a very powerful decomposition theorem, and captures a lot of information that would be otherwise difficult to deal with. So let me start. Of course, we won't be able to recall everything that we need, but let's recall at least a few things that we will need to follow this lecture. So again, we have some endomorphism on a vector space V. Then for any arbitrary vector in the vector space, we defined the cyclic degree of V, and this was a non-standard terminology, as the dimension of the cyclic subspace generated by the vector. And we noted that the cyclic degree of V is nothing but the smallest non-negative d for which these are linearly dependent. Okay, well, this makes sense, I guess, only when V is non-zero. If V is 0, then cyclic degree of V is 0. So let's not worry about that. Okay, we have this fact, call it a theorem or a lemma. We proved it, which says that if you have an endomorphism and Px is an eigenpolynomial of it, and V is a generalized polyeigenvector of it, corresponding to the polynomial Px, which should be written in the statement, corresponding to Px, then the cyclic degree of V is, first you find the smallest k for which this happens, and such a k must exist because V is a generalized polyeigenvector. And then you multiply that thing with the degree of the eigenpolynomial. Okay, so in case of generalized polyeigenvectors, there is a better handle on the notion of cyclic degree than, or rather a different handle on the notion of cyclic degree than what is afforded by the definition. Okay, and of course we will use the primary decomposition theorem like we do in every lecture. All right. Here are two problems for practice. And now let us get started. So what is the theorem? What is the cyclic decomposition theorem? The theorem says that for any endomorphism on a vector space V, and again everything is finite dimensional, there is a cyclic decomposition of V. What does that mean? It means that there exists some finitely many vectors in the vector space such that the corresponding cyclic subspaces form a direct sum decomposition of the vector space V. So pretty impressive and powerful theorem. You can break up the vector space V into cyclic subspaces. That's just amazing. All right, and before we proceed, let us just note, by virtue of the primary decomposition theorem, we need to prove it only for the space of generalized polyeigenvectors. So what I'm trying to say is that we may assume, without loss of generality or by virtue of the primary decomposition theorem, in order to prove this theorem, we may assume that there is only one eigenpolynomial of T, because you can pass to the space of generalized polyeigenvectors corresponding to a given eigenpolynomial. All right, so this is essentially what we will do. We will prove it this is sort of the way we will go about it. Essentially, that is the way we will go about it. We will prove it when T has only one eigenpolynomial. Okay. So before that, we will fix up some notation. So we have some arbitrary endomorphism and Px is an eigenpolynomial of T. We will write S to mean the saturation exponent of P. We will write Vs to mean the space of generalized polyeigenvectors corresponding to the eigenpolynomial P. And for any vector V, we will write Zv to mean the cyclic subspace generated by V corresponding to the endomorphism T. Since we are not going to be dealing with two different endomorphisms, we have shortened the notation. I think I might even prefer V in the subscript. That would look even better. Okay, there is another terminology that we will introduce. For any vector V in Vs, meaning for any generalized polyeigenvector corresponding to the eigenpolynomial Px, we will define the order of V as, the notation is this, and the definition is you take the cyclic degree and you divide it by the degree of the eigenpolynomial. And this is an integer because of what we recalled. This is degree px times the smallest k, the property that ptkv is 0. So this is a multiple of degree of px, and hence this ratio is an integer. So this is merely a change of, instead of using this, we will be just kind of normalizing it. This is a pesky factor that will appear. So just to normalize things, we have defined this new notion. Again, this is non-standard. This is not there in any textbook or anything. Okay. Now, here are two exercises associated with these concepts. So for any vector v in Vs, if the order of that is written as k, and suppose there is some polynomial fx such that the corresponding endomorphism kills the vector v, then what we have is px to the power k divides fx. Okay, so that's that. And there was the second one, but yeah, well, okay, maybe we will not need the second one, but let me complete it. So for any two generalized polyeigenvectors corresponding to the eigenpolynomial px, and suppose u is non-zero and pt of v is u, then order of v is order of u plus 1. In fact, here I think all we need is the non-zeroness of v rather than u. But anyway, let me state it this way. All right. So now we will move to the proof of the cyclic decomposition theorem. And here is the first preparatory lemma, or the special baby case I've written of a certain preparatory lemma. We will see it next, but let us see the proof of this in full detail. So what are we saying? Fix a generalized polyeigenvector corresponding to Px, and suppose its order is maximum possible. The order of any generalized polyeigenvector is at most S. S is the saturation exponent, so you cannot go beyond that. So suppose you have an generalized polyeigenvector with the maximum possible order, and there is one such thing. One such thing always exists. Okay, and pick anything in the corresponding quotient space. So when I say corresponding quotient, I mean just quotient by the cyclic subspace generated by V. Okay. So pick anything arbitrarily in the quotient, and we have written it as u bar. So u is an element here, and u bar is the corresponding element there. Then we want to say that there is some other generalized polyeigenvector V prime such that its order is same as the order of u bar, and after going modulo the cyclic subspace, you are equal to u bar. This is somewhat trippy actually. So here I have noticed I have used the endomorphism also. When you define order, the endomorphism matters. So here when we say order of V prime, we mean with respect to T. And here it's with respect to T bar. U bar is an element here, and since this is a T invariant subspace, the endomorphism T restricts to this guy. So before I had, the notation that we developed was that T is already an endomorphism on V, and with respect to those notations we are talking. So we are saying that order of V prime in the parent thing is same as the order of U bar in the quotient thing. So T bar is an endomorphism on this guy, so you can talk about order of this guy, and we are saying that you can pick V prime in the space of generalized polyeigenvectors such that the orders of U bar and V bar are equal, and after you go modulo, v prime bar and u bar are also equal. Okay, now you may question, well, why can't I just take v prime as u? What is wrong with that? Well, this is clearly true if you take v prime as u, but this may not be. The order of u may be larger than the order of u bar. So this lemma is, the content of this lemma is basically simultaneously adjusting for this. Okay, enough about that. Let's prove it. So let's say the order of u bar is something. This is, let's say, s minus k for some non-negative k. Now it's going to be of this form because the order of anything here is at most s. So the order of anything here is also at most s. The saturation exponent of t is only dominating the saturation exponent of t bar, clearly. Okay? All right. So let's say the order of u bar is of this form, some non-negative k. So then by definition, this thing is 0, which implies this thing is in the cyclic subspace generated by V. Let me also put the endomorphism just so that there is no confusion. So what is happening here? Well, just note that the left side is nothing but the bar of this guy. This kind of thing we have done many times. So just notice this. And we get, by definition of the cyclic subspace, or by what we have done about cyclic subspaces, this is equal to ftv for some polynomial fx over the base field. Okay, and therefore this implies that pt to the s of u is that. So what happened? We just operated pt to the k on both sides. You apply pt to the k here and pt to the k here. The right side becomes that. The left side becomes that. Okay, but this thing is 0. This thing is 0 simply because u is, after all, living here. So s is the saturation exponent, and hence this has to be 0. Okay, so this guy is 0. And now by what we left sort of as an exercise when we were discussing the notion of order, this implies that pt to the s minus k, yeah, so just give me a second. Yeah, sorry. So what I was trying to say was the following. So we have that this thing is 0 and order of v is s. So now by what we recalled about order, this implies that px to the s must divide px to the k times fx, right? And therefore we get px to the s minus k divides fx. Okay, so we may write fx as ex to the s minus k times gx. All right, and now define v prime as u minus gt of v. And this is the key step. This is the construction that one has to come up with in order to solve this lemma. So we define v prime like this, and clearly then v prime bar is u bar because this is already lying in the cyclic subspace generated by v. So once you take the bar, this dies, and hence we have this. So we just need to now prove the second guy. So to do that, since v prime bar is u bar, the order of v prime bar is equal to order of u bar, and hence the order of v prime is at least the order of u bar. This already implies that order of v prime is at least the order of this thing, which is the order of u bar. So all I'm saying is that this inequality is trivial, and since v prime bar is u bar, we get that we have this inequality. So we just need to show that shear equality happens. So in order to prove it, we just need to show that this thing is 0. Once we do this, we will be done. But what is this thing? This is equal to, by definition of v prime, this is equal to, okay, all we have done is just substitute the expression for v prime. So we have that, but this thing is 0 because the order of u was s minus k by notation. That this part is 0. And note that this is f of t. No, this is not f of t. Wait a second. Yeah, this is f of t. Yes. So maybe I said something incorrect. This shouldn't. I said that this is 0, but wait a second. Yeah, sorry. This thing is ftv. pt bar s minus k u bar is 0. Order of u is not necessarily s minus k. Order of u bar is s minus k. So sorry about that. This thing is f of tv, and this thing is also f of tv because by definition of fx, this thing is f of t. So this is ftv minus ftv, which is 0. And that finishes the proof. So once again, this much was clear that this thing is equal to that thing, and all we need to do is show that this is 0. So once we have this expression, this thing is equal to f of tv because of this equation, and the second thing is equal to f of tv. So the two cancel out. The mistake I made was I said that this is 0, but that is not true. I kind of got confused because of that, but I'm sure now there is no confusion. Okay, so we have proved this lemma, and once again, let us read it out. It says that once you have an element of maximum possible order in the space of generalized polyeigenvectors, and you pick anything arbitrarily in the corresponding quotient space, but when I say corresponding quotient, I mean quotient by the cyclic subspace generated by this element, then you can achieve that element in a certain way. In which way? You can get an element in the parent whose order is same as the order of the thing living in the quotient space, and when you go modulo the cyclic subspace, you recover this element. It's a strange sounding lemma, but think about it. We have proved it anyway. Okay, so now the next thing will be a generalization of it. This is the preparatory lemma. Looks complicated, but here what we have is we have a sequence of things in the space of generalized polyeigenvectors satisfying a few conditions. The first is that the sum of the corresponding cyclic subspaces is actually a direct sum. And the second is that V1 has maximum possible order in this space of generalized polyeigenvectors. V2 bar has maximum possible order in the corresponding quotient. So this T bar denotes the endomorphism induced here. Then V3 bar has maximum possible order in this space, where this T bar is different from that T bar. This T bar is an endomorphism here, while that T bar is an endomorphism here. Unfortunately, this abusive notation cannot be avoided. Okay, and up to Vm, Vm bar has maximum possible order in this quotient. In the previous lemma, m was equal to 1. Here, m is some arbitrary thing. Okay, and now we pick Vm plus 1 bar here arbitrarily. Okay, and then the same thing. What we are going to say is that we can achieve Vm plus 1 bar in a certain way, meaning there is a vector in the space of generalized polyeigenvectors which recovers the element once you go quotient and whose order is same as the order of the thing in the quotient. There should be a bar here. So this is an immediate generalization of the previous one. In the previous lemma is nothing but it's same as this lemma if m were equal to 1. We have just generalized it, and clearly proof of it can be written using induction. Exactly the way the previous one went. It's just that notationally it is ugly. And I do not feel like repeating that argument, so I've written it up. You can read it by pausing the video. This is the first paragraph. There may be typos, I'm sorry about that. And this is the second page. So it's just the previous proof repeated inductively. It would be better to prove it yourself rather than look at this horrible thing. But in case you get stuck at some point or want to confirm something or get confused, you can refer to these writings. So I'm assuming you follow that lemma and understand its proof. And now I think we are in position to prove the cyclic decomposition theorem. Yeah, so to prove the cyclic decomposition, this is just the final lemma from which the cyclic decomposition would be a corollary. Okay. So what is this saying? The setting is the same as the previous lemma. We have v1 up to vm in the space of generalized polyeigenvectors such that the cyclic subspaces corresponding to them sum up in this fashion that they form a direct sum. The sum is actually a direct sum. And the same thing, v1 has maximum possible order here, then v2 bar has maximum possible order in the corresponding quotient, and so on up to vm bar. Then we are saying that there is some element in the space of generalized polyeigenvectors such that the corresponding element in the quotient has maximum possible order in this quotient space, obviously, and that the sum is the direct sum. Okay? So once we prove this, it should be clear that cyclic decomposition is a corollary. But anyway, if the statement of this lemma is not clear, pause the video and read it. And with that, let us now try to prove this. Okay. It's going to be a short proof. In fact, I encourage you to prove this yourself rather than look at my writing. Okay, so here is how we want to go about it. We want to construct or sort of deduce the existence of this little v. So we will pick something, call it vm plus 1, in the quotient of maximum possible order. Okay. All right. And by using the previous lemma, let v be such that v bar is vm plus 1 bar and order of v in the original thing is same as the order of vm plus 1 bar in the quotient. And let us say by notation that this is equal to s minus k for some non-negative k. Okay? Where k is non-negative. Alright, so far nothing has happened except that we have used the previous lemma. And so we claim that this v that we just found is a v satisfying all these conditions. So all we now need to do is justify this one because the previous one is already justified by that. We just need to show this and we will be done. Whoops. So we will assume that actually this sum is not the direct sum, which means that some vector here plus some vector there plus some vector here plus some vector here sums up to 0. And then we just want to show that each of them were actually 0. So since v bar is vm plus 1 bar, we get v minus vm plus 1 is living in this direct sum. Okay. All right. And now we go back to our goal. We want to show that the sum is a direct sum, meaning we want to show that this thing plus the cyclic subspace generated by v is actually this direct sum. All right. So say, maybe let me write it this way. This thing plus ftv is equal to 0 So what happened? We want to show that this sum is a direct sum. So what that means is you pick arbitrary vectors from here, which is same as that. So f1x up to fmx are arbitrary polynomials. And these are the corresponding evaluations or whatever you want to call it. So this is an arbitrary vector formed by summing, this is a vector formed by summing arbitrary vectors here. And this is an arbitrary vector chosen there. And suppose they sum up to 0. Showing this equality here is same as saying that you want to show that each of them are 0. Meaning each of these guys are 0 and this guy is 0. But it is enough to show that this guy is 0, because once you show this guy is 0, what you are left with is a sum of a bunch of things in a direct sum. And hence, each of them must be 0 by definition of direct sum. So all I'm saying is that enough to show that this is 0. Okay? Alright. But how do we do it? So this thing, once you apply a bar, this is going to be 0 bar. Why? Because of this equation. So using this equation, you see that ftv bar is 0 bar. ftv lies in the direct sum, so ftv bar is 0 bar, which implies f of t bar v bar is 0 bar, which implies this thing divides f of x. Why? Because the order of v bar in the quotient is same as the order of vm plus 1 bar, which by notation was s minus k, and why this division happens was left as an exercise. Okay, so we have that. Yeah, so finally, we have so we also have that this is equal to the order of v in the original thing, right? This is how the vector v was chosen. So let me show it. We had v such that v bar was that thing, and the order of v in the original space was same as the order of the thing in the quotient space. So the order of v is same as the order of v bar. V bar is same as vm plus 1 bar, but this equality is the magic thing that was provided by the previous lemma. So the order of v is also same as s minus k. So this implies that ftv is also 0, right? Because fx is divisible by this guy and order of v is s minus k. So this must be 0, and that's it. That finishes the proof. Let me write. Right, so that proves the cyclic decomposition theorem. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.